Good morning and welcome to NCSA Center for Artificial Intelligence Innovation Spring Seminar Series. My name is Melanie Moore and I'm one of the project managers here at the center. Today's presentation will be by Dr. Kunle Olukotun. Kunle Olukotun is a Cadence design professor of electrical engineering and computer science at Stanford University. Olukotun is known as a pioneer in multi-core processor design and a leader of the Stanford Hydra Chip Multiprocessor CMP research project. Prior to Sambanova systems, Olukotun founded Afera web system to develop high throughput, low power multi-core processors for server systems. Afera multi-core system processors called Niagara was acquired by Sun Microsystems. Niagara Drive processors now power Oracle's Spark-based servers. Olukotun is the director of the Pervasive Parallel Lab and a member of the Data Analytics for What's Next Dawn Lab, which is developing infrastructures for usable machine learning. Olukotun is an ACM Fellow and IEEE Fellow for contributions to multi-processors on a chip in a multi-threaded processor design. Olukotun recently won the prestigious IEEE Computer Society Harry H. Goody Memorial Award and was also elected to the National Academy for Engineering, which was one of the highest professional distinctions accorded engineers. Kunle received his PhD in computer engineering from the University of Michigan. Welcome, Kunle.
Thanks, Melanie, and glad to be here this morning or afternoon, depending on your time zone. So thanks for inviting me to talk to you. Pity I can't be there in person, but of course, traveling's not happening at the moment. So today I want to talk about data flow optimized systems for AI and the work that we're doing at Sambanova, which is an outgrowth of ideas that were developed at Stanford with on research programs, and so it's always good to be talking to people with academic backgrounds because, of course, I have an affinity for people like that. So when we founded Sambanova Systems about 3.5 years ago, my co-founders Rodrigo Liang and Chris Ray thought about sort of how we could transform the computing landscape for AI and machine learning. And so that was a goal. And it was kind of informed by 3 computing trends that we realized. One was this notion that multi-core processing capability and the idea of putting more and more cores on a chip as a way to improve performance was basically running out of steam. And I say this, having been one of the pioneers of the whole multi-core approach in the 90s, but it was clear that, the processes themselves were inefficient, and putting more and more cores together on a single chip just added to the inefficiency. And it didn't matter whether these cores were, fat cores like CPUs or much more optimized cores like GPUs. The second computing trend was this notion that of the convergence between machine learning training and machine learning inference, right? Traditionally, you think of GPUs as the accelerator for training, and then inference is done on CPUs because they're much better at batch 1 inference. And our notion was that, you could really bring these things together and get a lot of advantages by doing that. Then lastly, this notion that, we need next generation compute to accelerate various applications, ML and AI being one of the most driving applications, but the whole notion that the next generation compute should really accelerate the broad range of computing that we want to do. And this was all informed by the idea that the future of computing was really data flow, right? So it was clear if you look at machine learning applications from medical imaging to natural language processing to recommender systems, you can clearly see the data flow ideas, and I'll elucidate, give you some more detail on that. But if you look at traditional sorts of computing that goes on, so data processing and high performance computing workloads, there also can be construed or formulated as data flow computing problems and accelerated by building a machine that was building an architecture and a system optimized for data flow. So what exactly did we think was needed in the next generation AI computing platform? Three key components, which I will basically be the structure of the rest of the talk. First is build the best AI processor, right, with both the highest absolute performance. Performance is very important, but even potentially more important is being able to get that performance in a very efficient way, right? Efficient in terms of resource usage, both energy and chip resources, and that it be flexible to accommodate the wide variety of machine learning models that are being developed and the innovation that's happening in the whole AI and ML space. And then secondly, second component would be an integrated software stack that could take the models being developed in the high-level frameworks and optimize them and transform them to run very efficiently in this data flow manner, and also enable the system to be deployed in cloud environments. And so what you want is an environment that is flexible and allows multiple users to effectively use it. And then finally, the development of state-of-the-art models that can really solve problems that are being that come out of various verticals, be it healthcare, life sciences, engineering, astronomy, and business, figuring out the state-of-the-art models that can really solve the problems and provide solutions that enable people in very problems to be solved that lead to greater efficiencies and greater capabilities. And so the way that we are approaching this problem of developing these three core components of what we're doing at Sambanova is a vertically integrated approach that crosses the boundaries of the stack, right? All the way from innovation in AI and ML algorithms to new compiler technologies focusing on transforming data flow into highly efficient computing, an architecture that is fundamentally and naturally configurable for very efficient use of the hardware, but also configurable in a data flow manner to take advantage of the computing paradigm that I said is most prevalent in the wide variety of ML and other high performance computing applications. And then lastly, a VLSI implementation that uses the latest implementation technology. And so what we want is optimization across these different layers to attain very high efficiency and flexibility at the same time. And we'll see how that plays out as I describe these three core components of the Sambanova system. This is the stack, right? From algorithms to compiler to architecture to VLSI, and the fact that we optimize across the stack, across the boundaries in order to get the very highest efficiency and flexibility for the systems that we're building for AI, ML, and other compute acceleration. Okay, so starting with the best AI processors. So how do we think about developing that? So key to the notion of AI is that sort of models are the new code, right? So if you think of traditional software development, which people have called software 1.0, you know, it's written in high-level languages, C++ or Java and the like, and it requires humans to kind of develop algorithms for different components of the system, right? And then to compose these together. Contrast that with, you know, ML and AI development, which is being called software 2.0, where you are taking a problem and you are you're building a model to solve that problem, and the weights of the neural network are really the code, right? And so it's really about the data driving the software development process, right? And so you think about how these neural networks look, and what you get is a data flow representation, right? Where you've got different kernels, in this case, a vision model composed of convolution pools and norms and some other kernels. And what you get is a dramatic decrease in the amount of code that's required. In this example, Google shrank their language code from 500,000 lines of C++ to 500 lines of Dataflow code in the form of TensorFlow. And what we see is that there are these high-level problems such as language translation, vision recognition, and robotics, which are being used, which these neural network software 2.0 approaches are being used. But that's not. But it's also being software 2.0 approach is also being used to tackle more mundane system level problems that we've had all along, right? So in this case, in the database arena, learned index structures. You can learn a database index by using machine learning training. You can use it for doing data cleaning. You can also use it for actually curating data and making training data more accessible. And of course, if you look at the AI for science realm, there are lots of people developing surrogate models to improve the performance of simulation and engineering models, right? And so the use of AI and machine learning is transforming the way that we do scientific and business sorts of computations. And as I said, this all looks like data flow. And the data flow is represented in the frameworks that are used to develop these models, right? And today, the dominant models, dominant frameworks that are being used are PyTorch and TensorFlow. And if you look at the domain-specific representations of the problem in these frameworks, that could be composed of kernels that are representative of the particular sort of machine learning application area. It turns out that from some early research we did at Stanford, that you could take these domain-specific operators like convolutions, matrix multiply, normalizations, and so on, and convert them into more generic parallel patterns, such as map, reduce, group by, and filter. And these parallel patterns can be composed in hierarchies and could form the basis of a compiler framework that can be used to optimize these machine learning algorithms. And it's also true of other data processing domain-specific languages like SQL, right? Where you have filters and joins and your data structures are tables, but they could be decomposed into these parallel patterns. And just to say a little bit more about parallel patterns here, so parallel patterns that you're typically familiar with are like map and reduce, but of course there are others like zip and flat map and group by. And the idea is that these patterns tell you about both the computation, the parallel computation characteristics of the pattern, but they also tell you about the data access, right? And so with these two components, then you can build very sophisticated compiler transformations that can optimize both the parallelism and locality of your application. So what kinds of capabilities should next generation AI systems support? Well, I made a case that sort of this hierarchical parallel pattern data flow is a natural model for executing these ML, AI, and other sorts of applications. The other big trend, of course, in ML and AI is the use of very, very large models trained on huge amounts of data to get, to increase the accuracy of the models, right? So terabyte-sized models is a driving trend in ML and AI. In order to deal with the huge amounts of model size that you need and the huge number of parameters, and still have tractable amounts of computation, sparsity is becoming more and more something that we see in these neural networks. Sparsity, both to kind of minimize the amount of data you need to model large dimensional matrices, but also to better model the real world, right? To model people, places, and things. These are naturally modeled by these graph neural networks, which means sparsity. Another key component that you need in next generation AI systems is the ability to support flexible mapping of these models to your architecture, right? So we think about taking these machine learning models and mapping them in terms of model parallelism, which I will explain in more detail in just a moment, but also in terms of data parallelism, which is kind of the natural, obvious things that do run these models on multiple sets of data at the same time. And then lastly, the whole notion that ML doesn't just sit by itself as an island, but it's surrounded by other kinds of computation, such as data processing and graph processing. And so the ability to accelerate all of this together means that you only need one accelerator and you can keep all the data in one place. And so this has lots of advantages. And so given these needs, what we came up with was the idea of a reconfigurable data flow architecture. And this reconfigurable data flow architecture is really a way of taking these parallel patterns and natively providing the capability to run these parallel patterns effectively and efficiently in hardware. And then the other component that we have is the ability to reconfigure the way that these parallel pattern components are put together to match the data flow of the application. And so the key components of the reconfigurable data flow architecture are pattern compute units to do the compute, and then pattern memory units to provide the data and to provide the communication between the compute, and then ways of accessing off-chip memory. And so you've got a tiled array of these pattern compute units and pattern memory units, these configurable components that can be configured together but using the on-chip network to match which are basically program switches to match the needs of the application. And this is key because it means that you can very efficiently, because you are configuring instead of executing instructions, you don't have that overhead of fetching, decoding, and dispatching instructions every cycle. And then because you configure the data flows between the different components, you make the communication very efficient, and you don't need to go on and off chip to access memory to provide the communication between the different kernels. And we'll see how this makes things a lot more efficient in just a moment. So the first realization of this reconfigurable data flow architecture is the Sambanova Cardinal SN10 reconfigurable data flow unit, RDU, and it's implemented in 7 nanometer TSMC technology. It was the first ML chip to be implemented in this technology. It's an impressive chip with 40 billion transistors, over 50 kilometers of wire, hundreds of teraflops, which are usable because we map very efficiently, hundreds of megabytes on chip, and direct interfaces both to other Sambanova chip, RDU chips, and also to off-chip memory. And of course, one chip is just one chip, and what you want, of course, is a collection of these chips that can be used to solve very large problems. And so we've got multiple chip systems, and these systems are deployed in standard racks with standard power and cooling, and a standard Linux-based operating system to provide interfaces to the rest of the data center, right? And so we have kind of 3 systems: small, medium, large, at least in a single rack. And then, of course, we've got multiple racks, and each of them, the smallest one has 8 RDUs, the next one has got 16, and the biggest one has got 32 RDUs. And what's more impressive is the amount of memory that we have, 19 times 19, or even larger times the memory that we can have in these systems compared to NVIDIA DGX A100. And the important thing, of course, is to be able to use this memory effectively to solve large problems. So that is the AI processor. It's a reconfigurable data flow unit that provides very high compute capability and very large memory capacity. And so the key to making this all useful, of course, is the integrated software stack. And the integrated software stack is what we call SambaFlow. And SambaFlow starts with the frameworks, right? The frameworks are where the models get defined, and they are either PyTorch or TensorFlow. And then once you represent your model in these frameworks, what you naturally get out is a data flow graph of machine learning kernel operations. And then there are lots of things that you want to do in order to optimize this graph to run on our Sambanova RDU chip, right? So we might want to figure out how we're going to execute the data flow graph. Are we going to execute things in a model parallel fashion or in a data parallel fashion? We might want to do a lot of optimizations at the parallel pattern data flow level. So tiling, figuring out how much parallelism to exploit, how to stream the computation to make effective use of the computational units. And so the goal is to take a PyTorch graph, such as the one on the left here, and map it to something that is efficiently laid out in space on the RDU chip or across multiple RDU chips in a system. And so the SambaFlow spatial compilation is to make this very efficient by moving by both figuring out how much parallelism and locality to exploit, and then mapping that that layout, that representation of the compute in terms of these parallel pattern compute units and pattern memory units, so that we minimize the communication between the different components of the data flow graph. So here's an example where we take a vision model, for a piece of a vision model, and we map it to the RDU by mapping the different kernels in space and having the kernels communicate using the on-chip network, right? And so the spatial mapping does 2 things. One, of course, it keeps the communicating components close together on a chip so that they communicate very efficiently. And it also means that you don't have to go off chip to do the communication. And because you are executing, all the kernels are laid out spatially and executing all the time, you don't have the overhead of initiating a new kernel on the accelerator every time that you have to start executing the next kernel, because they're all laid out in time. So this has the
impact of dramatically reducing the off-chip bandwidth and keeping the utilization of the on-chip compute very high, right? And so the whole idea then is that you've got your data flow graph of machine learning kernels, machine learning operations, and you want to map it down to something that runs very efficiently in space on the RDU. And there's this huge design space that you have to potentially traverse in order to come up with an efficient mapping. And you want to do this quickly, of course, because you don't want to wait days for the compilation to finish, right? And so there's all these decisions that have to be made about, how you're going to do the mapping, how much tiling you're going to use, how much parallelization you're going to use, how much intermediate memory for the how much memory for the intermediate tensors, and when you access the DRAM. And the compiler makes all these decisions in a pretty optimal way to get you very efficient performance. And so to contrast this with how things are done today on GPUs, right? And GPUs can only run one kernel at a time. And so what happens is that if you're running the data flow graph shown here at the top, first you would do the first convolution. The first convolution would complete and put its results in memory, off-chip memory, and then you would fire, the host would get involved, and the next kernel pool would be executed, and then the pool would get the results from the off-chip HBM, pull them in, start executing, and dump its results to the off-chip HBM, and so on, right? And so what you get, of course, is the need for lots of off-chip memory bandwidth and the overhead of initiating the kernels. And so in the data flow spatial way, we lay the compute units out in space, and we move the data very efficiently from one kernel to the next, removing the need for off-chip memory access. And as we'll see, keeping the computational units busy all the time for much higher utilization, right? So this is kind of these key ideas of, data flow computing is match the data flow of the application and keep all the units busy all the time while minimizing memory bandwidth, right? And one of the key ways we do that is by exploiting what's called model parallelism, right? So let's see how this works. So model parallelism has been explored by both Microsoft and Google at a coarse-grained level, right? And so the whole idea of model parallelism is that, if you have a limited amount of GPU memory and you want to run a model that's too big for one GPU, you can put multiple multiple sections of that model on different GPUs, and then you can move the data as you are processing or training from one GPU compute unit to the next, right? So in this example, we have four forward sections, and then correspondingly 4 backward sections in our training algorithm. And the forward sections basically compute the loss, which is used by the backward sections to compute the gradients, which are then used to update the weights. And then you go through the forward sections, and of course you keep going until things converge. All right. And so if you look at the operation in time, as we see here, first we do the forward sections, and then we do the backwards section, right? Backward section. And what you need to do then is update the weights, and these are shown here in this vertical set of updates. And typically what happens is you need to make the synchronous algorithm waits until you all the backward sections are finished before you update the model, and then you begin executing the forward sections on a new mini batch of data, right? And so the synchronization barrier is a basic limit then in your performance, because it means you can't start a new mini batch until the old mini batch has finished its updates, okay? And so this is the synchronous execution, right? And what we see here, right, is this constraint of the synchronization barrier limits when the next mini batch can start, right? And so, if you look at this, right, and you're an architect like me, you say, hey, we've got all of these sections that are only being used, one at a time in a sequential fashion. So the next thing that you want to do is pipeline this operation, right? So let's pipeline it and get some more performance, because that's what architects do, right? And you kind of reminded of executing instructions in a CPU pipeline, right? And we know that, hey, if we pipeline more deeply, we can increase the rate or throughput of our pipeline. And of course, the limiting factor in executing instructions are what are called pipeline hazards, right? You've got control hazards due to branches and data hazards due to the fact that, that instructions communicate among one another, right? However, to a first order, if I, pipeline more deeply, I get higher throughput. How about in this training pipeline? So what happens is, we can keep increasing the number of pipeline stages, but because of our synchronization hazard, we're just gonna basically get lower and lower utilization. So we don't get any improvement because we have this fundamental hazard, which is limiting performance. And so the question is, what can we do about this? Well, in working with Chris Ray over the years, one thing he taught me about machine learning is, you need to relax, because it's only machine learning. And so what kinds of relaxation can you do? What kinds of relaxation have we explored? Well, we've explored the idea of using smaller integers and get to advantages of higher, less energy and being able to do more compute. His big innovation was this algorithm called Hogwild, which said if you were trying to do training using the stochastic gradient descent algorithm, that you didn't need to synchronize in traditional ways, that you could get rid of the synchronization and you would still have your algorithm converge roughly in the same time to the same answer. We've looked at sort of relaxing cache coherence, right? The fact that, hey, again, stochastic gradient descent is this stochastic algorithm, and you don't need coherence all the same, working all the time. And you could, not have your coherence algorithm, you could have it drop a large percentage of the coherence messages and still get the right result. And so the whole idea is that by doing this relaxation, you can get higher or better hardware efficiency, so more efficiency, but not adversely impact the accuracy of your algorithm, or the fact that it converges to the right answer. So using this idea, we could apply this to pipelined training, and instead of updating the model at the end of the pipeline, we can update the model as soon as the particular backward step or backward section is complete. And so that's shown here, where we are, updating the weights as soon as we finish the particular backward step or stage. So after B0, we do an update. After B1, we do an update. After B2, we do an update, and so on. And then we start executing a new mini batch. Immediately we finish one step of the previous F0 stage of the previous mini batch, right? And so this is great because now we have our throughput equal that matches the pipeline depth, right? And so the problem is, of course, that we've got this update that happens, these updates that happen in an asynchronous manner, right? So for instance, if we look at mini batch 6, right, you know, it gets some of its weight updates from M1 for stage F0, and the backward stage gets its update from mini batch 5, right? So for a delay of 4. And then if we look at M6, it gets its M6. We look at stage F1, right? It gets its forward update from mini batch 1. So and it's backward update from mini batch 5. So anyway, you've got these different delays and depending on the particular stage. And what happens when you do this? Well, if you do this and you don't do anything else, what you get is a training algorithm that doesn't work, right? And basically what you get a result which is no better than random guessing, right? So this is the naive asynchronous algorithm doesn't really converge, right? So the synchronous algorithm, you know, converges to a test accuracy of 95%, and the naive algorithm converges to a test accuracy of 10%, right? So that's pretty lousy. And so what can we do about it? Well, what you need to do is you need to scale your learning rate to match the delay, right? So if you've got a large amount of delay in your asynchrony, then you need a small learning rate. If you've got a small amount of delay, then you can use a much larger learning rate, right? And if you make this change to your learning rate to accommodate asynchrony, all of a sudden things start working correctly, right? And so what we see here is that both with the vision model, ResNet 50, the asynchronous algorithm in orange here matches the test accuracy of the synchronous algorithm. And it's the same for this transformer-based language model. So both of these models converge to the same answer using the asynchronous pipeline model. And so, of course, we get what we want, very high throughput by pipelining our training pipeline, but also we also get the accuracy that we want. One of the other benefits of the reconfigurable data flow is you don't have the unpredictability of caches and instruction execution, and so you get very, very repeatable execution, right? And so this just shows the magnitude of difference for the RDU versus the GPU. Essentially, no difference between from run to run in the RDU, and significant differences in the GPUs. Okay, so we talked about both the hardware and software. So what sort of models, state-of-the-art models, does this combination of data flow hardware and new compilation strategies enable? So first of all, kind of three large models that we're focusing on. One is sort of very large parameter natural language processing models. We know that these large parameter models like GPT-3 and so on have huge capabilities. You know, they kind of when people see the capabilities of these models, they're completely stunned, and that's enabled by trillions of parameters. Also, very high resolution models, image models, right? So, you know, you want these high resolution image models for astronomy, medical imaging, X-ray imaging, and the like, and these are not easily handled by current GPU-based systems. And then lastly, huge recommendation models, which are the backbone to internet services, right? So Facebook, you know, Amazon, Netflix, all of these large internet services require recommendation capabilities. So starting with the large language models, by having huge amounts of memory, 20 times the memory that you can put next to a GPU on an RDU, you can enable, you know, on a single system to be able to train these huge models, right? And remember, the key to being able to use the lower bandwidth DRAM is because we spatially arrange the computation on chip, and we dramatically use much less off-chip bandwidth. And so the benefit now is, of course, we can get much higher capacity with DRAM, but then also be able to use the compute much more efficiently. And so this enables us to put these trillion parameter models on a single 8 RDU system and train these models effectively. And so what we've been able to do is to take all of Hugging Face, which is kind of the place where these transformer-based models, you know, there's a wide variety of models, and it's a place where most developers of transformer, of natural language processing-based systems go to for models. And we show that, you know, with the data scale system, we can match the accuracies of these models compared to a DGX A100, but again, using much smaller systems because we've got the ability to have much larger memories. In the image recognition area, what we see is that most of the research that has been done to date, you know, the ones that people are most familiar with, the ImageNet, are basically low resolution images, you know, 224 by 224. Most of the images, of course, you take on your phone are like 4K images, but of course, they're actually processed at much lower resolution. But for real hard science and medical imaging problems, you really want very high resolution, up to 50K by 50K. And this is something we can do on a Sambanova RDU system because we have very sophisticated tiling capability that can take a full, in this case, 40K by 40K image and break it into tiles and then execute those tiles, build the model based on the individual tiles and stitch them together in such a way that you lose no accuracy, right? And so this is something you simply can't do on GPUs today, and even on CPUs. If you try and do this from PyTorch, you actually will get a runtime error and it won't execute. And so just to kind of be clear about how this works, right? Of course, convolution is an operator that has creates a moat around each operation. And if you do not tile correctly with the right kind of overlap, then what you'll end up with is what we see at the top row here. We'll have a image that is a model that it has gaps in it, right? However, if you tile correctly the way that we do things with the Sambanova SambaFlow system, then what you'll get is an output that does not have any gaps or any motes in it, and you'll get the accuracy that you can hope for over the whole image. And this has real impact on the accuracy that you get, right? So this just shows that even if you go from that by going to an image which is 4 times as big, we get higher accuracy on the RDU, right? And we've got some recent results showing for medical imaging, showing dramatically better capability in detecting early stage cancer by using higher resolution images than you can actually process with on a GPU. So higher resolution imaging is a key component. Another area, last area, is this idea of large recommender models, right? And so recommender models are kind of the core of a lot of internet services at Facebook. Roughly 80% of the compute inference capability is recommenders, right? And recommenders, the key to accuracy in recommenders is the size of the embedding tables, which kind of capture user preferences, right? And so this shows that the training accuracy gets better as you increase the size of the embedding dimensionality and the size of the embedding table for multiple different kinds of benchmarks, Kaggle and Cryo-TB. And this shows that with the Sambanova systems, you can get high performance with very, very large embedding tables, right? And these are embedding tables that simply won't fit on a GPU, and on a CPU, the performance is not very good. And so, in looking at this benefit of large memory capacity and efficient use of compute and efficient use of bandwidth, gives you these fundamental improvements in throughput and latency on recommendation problems, right? So here, in terms of throughput, we're kind of 20x better than an A100, and much lower latency, right? And this, of course, is using both kind of batch one, right, where there's a dramatic difference, but also even in much larger batches where you'd expect a GPU to start to have more advantage. Traditionally, in inference, of course, what you really want is the best performance at batch one, because the assumption is that you're only going to get one request at a time, and you can't batch up requests because, of course, that would just increase the overall latency of your response. So to conclude then, AI computing is of course, multifaceted and complex, and it has a number of components that we focus on at Sambanova. Number one being performance, of course. We have a number of new world records, but of course, performance is just really a means to an end, and what you really want is high accuracy, right? So that you can get state-of-the-art accuracy on the models that you care about, and actually training these models and serving these models needs the ability to scale to large numbers of RDUs, huge amounts of memory, and of course, this has got to be delivered in multiple systems. And so the ability to scale, and to scale both in the hardware and the software, are kind of key components of what we're developing at Sambanova. And then lastly, ease of use, right? So when we delivered our systems to both Livermore and to Argonne, within the hour, the researchers were up and running models and training models to new levels of accuracy, and inferring with new capabilities. And so at the end of the day, it's about what models can you develop for your particular use cases, and how flexibly can you accelerate not just your ML component, but other components such as data processing on your accelerator. So that's what we're focusing on at Sambanova. So with that, I'll end, and I'll be willing to take any questions that you have. Thank you.
Kunle, there are a couple of questions in the chat that came throughout.
Yeah, so the good question is Dataflow architectures were not successful in the 80s. So Dataflow is kind of an overused word. So the Dataflow of the 80s was a very fine-grained Dataflow where we were looking at data flow between individual instructions. Here we're looking at data flow between kernels of computation. And what's important then is really how the data, be it tensors or tables or graph elements, flows between one kernel and the other. And the problem with CPUs and GPUs is they say a lot about the compute, but they don't really allow you to control the data movement very precisely, right? You typically rely on the automatic memory hierarchy, or you have very high overhead messaging mechanisms, right? And so what you want with a natural data flow implementation, reconfigurable data flow, is to be able to, with very, very low overheads, communicate between one kernel and another. And so that's what we provide on the RDU. And so, we could go into details about why the data flow architectures of the 1980s were not successful, but suffice it to say, this is not your father's data flow. This is kind of a new imagination. You might call it coarse-grained data flow that actually works quite well for these applications. Okay, so yeah. Yeah, so the answer is sort of on relaxation, it's not a free lunch. Yeah, so you need to track things and make sure that things are not diverging. But it turns out that for the cases that we've looked at, most of the cases we've looked at, that you don't see divergence if you control the learning rate appropriately. Yeah, so the question is about how scalable is the image tiling? What is the limit? And there is no limit. The limit is the amount of compute you have, how long you're willing to wait for the answer. But in terms of the approach to tiling, you can do any size image that you want. You can just tile it appropriately. And if you handle the overlaps correctly, you'll get the same answer as you would have if you process the whole image in one go. Could you provide some details on the capabilities of the PCU, how much on-chip SRAM exists? We're not actually disclosing that at the moment. How does the system compare against other new systems like the one from GraphCore? We don't know precisely what the GraphCore system looks like. The focus, our focus is on systems that you can readily get in the marketplace, and so that's NVIDIA V100 and NVIDIA A100. So we don't have any comparisons with GraphCore. Has Sambanova submitted to the recent ML Commons benchmark? How does Sambanova compare against the inference? So Sambanova has not submitted to the ML Commons benchmark. Our focus has been on solving the problems of the initial set of customers that we have. And so that's where all our efforts have been going into. In time, of course, we will spend some efforts on making a submission for the ML Commons. But of course, as you know, this takes a significant amount of resources. And given the fact that we're a startup, we want to focus on satisfying our customers.
We are at the top of the hour, so thank you very much, Kunle, for today's presentation.
Yeah, thank you. And thanks for the questions. Lots of insightful questions.
All right. Thank you, everyone, for joining.